Good morning, my dear friends. Let us discuss the GATE question paper on instrumentation for the year 2020. In the last two videos, we have seen GATE paper for ECE, for electrical. Okay? And in this session, we'll see the questions, how they're given in for instrumentation. This was held on February 6th, 2022, in the afternoon session. Okay? Based on the memory-based questions sent by the students, I have prepared this video. Okay, let us see one by one. In this video, we're going to see the questions on network theory, digital electronics, control systems, analog circuits, signals and systems, communications. Okay, a little bit maths also. Okay, we'll see one by one. Let us start the first question. This question, if you notice here, first question, in the band pass filter circuit shown, the given R naught equal to 50 ohms, this L naught equal to 1 millihenry, C naught is given as 10 microfarad. Okay, you can see this is L naught, okay, C naught, R naught. The quality factor of the circuit, they are asking us to determine the quality factor of the circuit. Okay, right. Here it seems like a series RLC circuit. Okay, something like a series resonant circuit. For a series resonant circuit, okay, if you know the RLC, what is the quality factor of the circuit for series resonant circuit? 1 by R root L by C. And here they given everything as R naught, L naught, C naught. That's all finished. This straightforward formula based question. You substitute these values 1 by 50 square root of 1 millihenry divided by 10 nanofarads. Okay. Or this is 1 by 50 square root of 1 milli means that 10 power minus 3, and this is 10 nano means 10 power minus 9. Okay, this is 1 by 50 square root of, when this 10 power minus 3, 10 power minus 9, this is 10 power minus 6 in the denominator, goes to numerator, becomes 10 power 6. Or this is okay, 1 by 50, 10 cube, square root of 10 power 6, nothing but 10 cube divided by square root of 10. Okay, just let us substitute. Okay, 1000 by 50, nothing but 20 by root 10. Just take the calculator and substitute this value. And if I substitute this value of Q, we are going to get something like a 6.324, something like 555, 32033. Okay, let us round up to two decimals here, and they're asking 6.32. That's all. If I extend this discussion, what is the unit of quality factor? Quality factor is the ratio of two energies, 2.2 energy stored by energy absorbed. Okay, energy dissipated. Nothing but ratio of two energies, nothing but no units. Okay, very good. Straightforward question from network theory. Okay, next. Okay, in the circuit shown, next question. We move on to next question. In the circuit shown, the load is driven by sinusoidal AC voltage source V1 equal 100 angle 0 at 50 H. Given R1 equal 20 ohms, C1, and they given L1 and R2, they're asking us to determine the power factor. Power factor for this circuit. Okay. Here, this also just is simplification we require. If the network looks like, say, some RC network, okay, and if you have R and some capacitor or inductor in series, okay, R plus JXL or R minus JXC, okay, then if you know the total impedance Z, you written something like R plus R minus JXL or JXC, then how the power factor is defined? Contribution of resistance to load to the total impedance, that is nothing but power factor. And if it is a inductive load, then the power factor will be lagging. If the load is a capacitive load, then the power factor will be leading. That's all. Time being, what you require to do is just simplify this network. Similarly, if the network looks like a parallel network, RL or RC, okay, calculate the admittance. Then contribution of conductive load G by total admittance will give the power factor. Right now, you do one thing simple, just calculate the impedance seen by the source. Okay? Since this element, all are connected in series, let us calculate the impedance seen by source. This R given as 20 ohms in the circuit. Okay, this is given as 100 by 1000 by pi micro. Okay, this R2 given as 4 ohms, L2, L1 given as 20 by pi. Let us do one thing. Let us convert the given network into phasor domain, okay, j omega domain. In j omega domain, C will become 1 by j omega C, L will become j omega L. Then what's impedance seen by source Z? This impedance seen by source nothing but this combination, this one, all are in series. Okay, this R1 parallel with minus j by omega C1 plus, okay, j omega L1 plus R2. Okay. Let us substitute those values. Okay. First, if I want to try to simplify, okay, or this also can be written as this is R1 parallel with 1 by j omega C1, okay, plus j omega L1 plus R2. Let us try to simplify this one. Yeah. First term, if I take first term, two terms, it seems like Z1, Z2 parallel, Z1, Z2 by Z1 plus Z2. This is 1 by j omega C1 divided by R1 plus 1 by j omega C1. Okay, plus j omega L1 plus R2, or this is R1 by 1 plus j omega C1 R1. Denominator, you have a numerator, you have by j omega C1, here also by j omega C1 cancel each other. This is j omega L1 plus R2. Okay. This is the impedance in Y source. Then let us substitute these values. What is the value of R1 given? R1 given is 20. This is 20 by 1 plus j omega. Okay. 20 by 1 plus j omega. What is omega given in the circuit? Omega is given as F is given as 50. Okay, if F is 50, okay, F is given as 50 here. Okay, this F is given as 50. That implies what is the value of omega? Omega nothing but 2 pi F. This 2 pi F nothing but 2 pi into 50, but 100 pi. Let us substitute that 100 pi. So 100 pi into C1. What is C1? 100 by 1000 by pi micro to R1. What is R1 given? 20. So this is about your 20. Next, plus j omega L1. J into omega. Omega is nothing but 100 by L1 given as 20 by pi milli. Plus R2. R2 nothing but 4. R2 nothing but 4. Okay. Therefore, what is the impedance in by source Z? Try to simplify this one. This is Z nothing but 20 pi. Okay, here this 100 pi, 1 pi cancel. 100 into 1000, 10 power 5. Okay. 1 plus j into 10 power 5 into micro is there. Micro nothing but 10 power minus 6 into 20. Plus j into this pi cancel, 2000 into milli. 2000 to milli. Milli means 10 power minus 3 plus 4. Okay. This Z. Yeah, let us try to simplify. Tell me what is the value of Z then? It's Z equal to 20 by. Okay, this is 10 power 5 into 20. Okay, 2 into 10 power 6. Okay, 10 power 6 into 10 power minus 6. This is 1. Okay, this is 10 power 5, 10 power 6 into micro, nothing but 10 power minus 6 into 10 power plus 6. Cancel each other. Okay, plus j into. Here also 1000 into milli, but cancel each other. It becomes. This is the total impedance in by source. Z equal to. Okay, that is. This Z, what is the Z we got here? This Z we got like 4 plus J2 plus 20 by 1 plus J2. Okay, what I am trying to do is let us separate the real term, separate the image term. This 4 plus J2, let us rationalize the denominator here. 1 minus J2 by 1 plus J2 into 1 minus J2. Let us multiply numerator denominator by 1 minus J2. Therefore, this is 4 plus J2 into 20 into 1 minus j2 divided by, this is a plus b into a minus b, here j, okay, a square minus b square, 1 square minus J2 whole square. Or this is 4 plus J2. Numerator we have 20 minus J40 divided by, this is 1 minus 4. J square nothing but minus 4. Okay, this is 4 plus J2 plus 20 minus J40 divided by 5. Or this is 4 plus J2. This is 4 minus J8. Okay, what is the total impedance seen by source then? This total impedance seen by source nothing but 8 minus J6. Okay, that's all. The impedance seen by source, whatever the complicated circuit given in circuit. Okay, here, what is the total impedance seen by source then? This is Z equal to 8 minus J6. And here it seems like some real part, some imaginary part. Okay, something like R minus J. If it is a plus sign is there, then it seems like R plus J omega L. Since it is a minus sign, it seems like R plus 1 by J omega say, or R minus J XC ohms. Okay. Right now, it seems like a resistor combination in series with the capacitor. Circuit nature is a capacitive. Capacitive. Okay. Then let us define the power factor. Power factor, how it is defined? Contribution of the resistor load to the total impedance. Okay. Here this is 8 divided by square root of 8 square plus 6 square. And here since the capacitor is a lead. Okay. Or this is 8 by square root of 64 plus 36, 100. But 10 lead. Okay. Answer. If you ask the magnitude, this is 0.8 lead. In the question, they asked us to calculate the power factor is dash. That's all. Only magnitude only. That's answer is 0.8 is the answer. That's all done. Okay, 0.8 is the right answer. Yeah, everyone? Very good. Let us move on to the next question here. What is the next question? Use the data given figure A. Okay, this question also belongs to circuit theory itself. Okay, use the data given figure A. Find the value of I3 in figure B. Okay. And if you notice here in the by these values, this R naught here also R naught same, 8 ohms, 8 ohms same, 4, 4 same, 6, 6 same, 8, 8 same, R naught same. Okay. And the only change here, they place a 16 volt source. Here they're asking us to determine I3, okay, when 8 volts and 48 volts is connected here. And here, if I notice this diagram, how it seems like, notice here everyone. This is some network here. Resistive network. Okay? It's a resistive network. Okay? Here also is the network. The same network here. Okay? Same resistive network itself. Same resistive network itself. From here, if I write simply instead of repeating that network again and again, the data, what is the data given? You notice here, they connected something like this. This is some 16 volts. Okay? This is some 16 volts. Okay? And here the current flowing this one. The output they are asking us something like this. This is a 48 volts. This is a 8 volts. Okay, this is 16 volts. Notice it. This is a resistive network. Resistive network. This is also a resistive network. Okay? Resistive network. For this resistive network, okay, what's the data they given here? This current is given as I1 equal to 2 amperes. Nothing but what is the current flowing here? This is the 2 amperes. This current supply by source nothing but 2 amperes. And here, what is the current flowing here? Okay, here is current flowing nothing but 1 by 3 amperes. They given this data. And for this one, they are asking us to determine the I3, nothing but current supplied by the 8 volt source, I3. I3. And here this is 48 volts placed like this. 48. That's all simple. They're asking something like this. Okay, let us give some number to this one. Let this be figure or figure A. We have to find this one. Okay, since the network is a resistive network, it will obey homogeneity principle. Nothing but it's a linear network. All homogeneity network. Okay, it's a linear network. All linear networks will obey homogeneity principle. If the excitation multiplied by constant k, response in all the branches of the network also getting multiplied by the same constant. Similarly, this is a resistor network. Resistor network nothing. A linear network, it's a passive network, it's a bilateral network. All linear passive bilateral networks will obey reciprocity principle. What do you mean reciprocity? Even by interchanging the source from input terminals to the output terminals, you get the same response. Okay, just I will transform to the next slide here. First diagram they given. Okay, this is for 16 volts. Okay, this is 16 volts. This current, what is the current given here? This is 1 by 3 amperes. What is the current flowing here? This is 2 amperes. This is figure A. It's a resistive network. Everything resistive. What they're asking us to determine here, for the same resistive network, here they placed a 1 voltage source, they placed another voltage source. Okay, here they placed a 8 volt source, so this is plus minus, so this is 48 volts. Okay, they're asking us to determine what is this current I3. Okay. So here, let us try to get the data for 8 volts at the input side. Let us get the data for 48 volts at the input side. And since the network is a linear network, bilateral network, it will obey superposition principle. Okay, right. Use the data here. What I'm trying to get, let us try to get the data for 8 volts at the input side. This is 16 volts. For the same network, let us apply homogeneity by 1 by 2. Homogeneity by 1 by 2. Okay, if the excitation multiplied by constant 1 by 2, response in all the branches also getting multiplied by the same constant 1 by 2. Okay, this is 16 into 1 by 2 is nothing but 8 volts. Okay, this response also becomes 2 into 1 by 2, 1 ampere. This response also becomes 1 by 3 into, okay, half. Okay, this also becomes 1 by, okay, half of that. 1 by 3 divided by 1 by 2. Okay, 1 by 3 divided by 1 by 2, 2 by 3 ampere. Okay, 1 by 3 divided by 2. Okay, so right. This is 1 by 6 ampere. This is 1 by 6 ampere. This becomes 1 by 6. Very good. One by 6. Everyone. Okay, right. Let us move on. Okay, right now for this one, this is 1 by 6 amperes. Similarly, let us try to get the data for 48 volts at the input side. Let this be figure B. In figure A itself, let us apply homogeneity by 3. Homogeneity by 3 times. Okay, by 3. If I apply homogeneity by 3 for that resistive network, okay, this is 16 into 3, 48 volts. And this response will become 2 into 3, 6 amperes. And this will become, okay, 3 times. Okay, 3 into 1 by 3, this becomes 1 ampere. Let it be figure C. What here, but in figure, okay, they are asking us to determine when this is 8 volts, what is current? When this is 8 volts, this current is 1 ampere. When this is 48 volts, what is this current here we require? Okay, since the network is resistive network, it will obey linearity, okay, passive bilateral network. All linear passive bilateral networks will obey reciprocity principle. Let us apply reciprocity. Reciprocity to figure figure C. Okay. If I apply reciprocity to figure C, okay, even interchanging the source from input terminals to the output terminals, if I apply 40 volt, 48 volts at the output side, if I short these terminals, I will get the same response 1 ampere here. Okay, this response nothing but 1 ampere itself. Let this be figure D. Let us apply superposition principle between figure A and figure D. Okay, figure D. Let us apply superposition between this figure B and figure D. Okay. Figure B superposition principle, SPT. Let us apply SPT between figure B and figure D. Figure B, figure D. For this resistive network, everyone following? Okay. Notice here. If I apply 8 volts here, 8 volts. What is current flowing here? This is 1 ampere here. If I apply 8 volts here, this current is 1 ampere. Okay, if I apply 48 volts from this one, okay, if I apply 48 volts here, what the current flowing here? 1 ampere. Then what is this current I3 in this direction? What is that I3 here? Tell me the I3 here. I3 in this direction. This current 1 ampere, this current 1 ampere. Okay. Then in this direction, 1 ampere flowing here. Okay. In the other direction, 1 ampere flowing here. Then what is the effective current in this direction here? Okay, 1 ampere minus 1. Okay, this I3, 0 ampere. Right. 0 ampere. That's all. You observe here, they are asking what is the I3. Use the data in figure A. What is the current I3 flowing in the circuit? Nothing but 0 amperes is right answer. 0 amperes is right answer. 0 amperes is right answer. Right? Very good. Everyone, excellent. 0 amperes is the right answer. Okay. Right. Complete first question, second question, okay, and a question on reciprocity principle. If you know reciprocity, this is easy, or else it becomes a complicated. Okay. So here they given some circuit diagram like this here. A resistive ladder, a digital to analog converter. Okay. This is a digital input that results in, okay, you don't bother about this D to A converter. Okay. Here they given it's a D to A converter digital input that results in the circuit having the state shown in figure. For this digital input, the Thevenin voltage and Thevenin resistance they ask you. The switches they given something like this. This is open circuit, switch A. Switch B is a short circuit. Switch C is a open circuit again, open circuit. And if you notice the effective circuit right now, okay, here this is connected to 2 ohms is connected to 2 kilo ohms connected to the ground. This 2 kilo ohms connected to 4 volt supply. Again, this 2 kilo ohms connected to the ground. Okay, if you redraw this one, how this circuit look like? This is a 2 kilo, this is a 1 kilo, okay, this is a 2 kilo ohms, this is a 1 kilo ohm, okay, this is a 1 kilo ohm, right? This is a 2 kilo ohms, this is directly connected to ground, this is a 2 kilo ohms, and this is connected to 4 volt supply, 4 volt supply like this, and this is a 2 kilo ohms connected to ground, 2 kilo ohms connected to ground, and this is the V0. Right now, this is grounded. Okay, right. Simpler. If I try to simplify this one, this 2K, 2K, both will be parallel. Okay, this point connected to ground, this point connected to ground. Okay, this resistor, both are parallel. Okay, 2K parallel to 2K. What is the equivalent resistance? R parallel to R, R by 2. Okay, this is R parallel to R, nothing but R by 2. 2K by 2, this is 1 kilo ohm. These two resistors parallel. Okay, now if I change this one right now, this is a 2K parallel to 2K. This becomes 1 kilo ohm. Now there is a 1 kilo ohm resistor in series. 1 kilo ohm. Okay. Here This is a 2 kilo. This is a 2 kilo ohm resistor. Okay, this is a 4 volt supply. This is 1 kilo ohm. This is 2 kilo ohms. Okay, this is grounded. This is a V0. They're asking us to determine the Thevenin voltage VTH RTH across as seen from the output node. Okay. If you look from this one, what is the VTH? What is the RTH? If you look from this one, what is the VTH? What is the RTH? If you look from this one, what is the VTH? What is the RTH? They're asking us to determine. And right now, let us try to simplify this network. This 1K, 1K both are series. This becomes 2K. Let's move on to next slide. Okay, 1K, 1K series. 1K series with 1K nothing but both R1 plus R2. This is 2 kilo ohms. Okay, right. This is grounded. Now, let us move on to this one 2K and 4K. Okay, this is 2K. This is 4 volts. Okay, next step. This is 1K. This is 2K. This is 1 kilo ohm. This is 2 kilo. Okay, this is the okay. This is the effective circuit here. They're asking us to determine the V0. Okay, if I simplify the simple question of solving for Thevenin. Okay, this branch is just I'm rearranging. Okay, this seems like a 4 volt source. This minus. Okay, this is plus 4 volts. This is grounded, right? Say 2 kilo ohms. This minus, this is plus, and this is a 2 kilo ohms connected to ground. This is a 1 kilo ohm. Okay, this is a 2 kilo ohms connected to ground. Simple. This is a V0. They're asking us to determine what is the VTH, what is the RTH. Okay, if you want to calculate RTH here, RTH. Okay. Deactivate the independent sources. This is a deactivate independent source. Okay, connect that source to ground. Okay, then this is a 2K ideal voltage source replaced by short. Okay, 2K. This is 2K. Okay, this is 1K. And this is 2K. That's all. Okay. Then tell me what is RTH seen here. Right now, these two resistors parallel, 2K parallel 2K. This is 1 kilo ohm. 2K parallel to 2K. This is 1 kilo ohm. Okay. This is 1 kilo ohm. It's a 2 kilo ohms, right? And this is RT. And again, this 1K 1K series, this becomes a 2 kilo. 1K series with 1K, nothing but 2 kilo ohms. Okay, this is a 2 kilo ohms. Right. Right now, this is the RTH we need to find. And again, this 2K, 2K both are parallel, right? Therefore, 2K parallel to 2K, nothing but 1 kilo ohm. It's RTH for the given flow. And if you notice the options here, B, D, you can eliminate, okay, which is given as 2K. Answer should be either A or C, 1K, 1K. Okay, we have to select between A or C. Let us calculate the VTH for the given question. VTH. Okay, how to find VTH here? VTH. Open the load, solve for VTH with respect to ground. This is a VTH. Okay, this is also VTH. Simple. Okay, it's your techniques here. You can apply your techniques. Simple. If you want to apply source transformation, you can apply source transformation. Voltage source series with resistor will become current source parallel with the resistor. 4 by 2K. Okay, this becomes 4 by 2K amperes. Okay, or 2 milliamperes. Parallel series resistor will become parallel resistance 2 kilo ohms. Okay, and here you have a 2 kilo ohm resistor. 1 kilo ohm resistor. Okay, this is a 2K. All are grounded like this. All are connected to ground. Okay, this is the V0 or VTH we need to find. And again, this 2K parallel, 2K parallel 2K, nothing but 1K, right? Now, it's a 4 by 2K. I will not simple, let it like this. And this 2K parallel to 2K, 2K parallel to 2K, nothing but 1 kilo ohm. And here, This is a 1 kilo ohm. This is a 2 kilo ohms. You have to find the VTH. Again, let us apply the source transformation for this. Current source for the resistor can be converted to voltage source series with the resistor. What's the magnitude of the voltage source? 4 by 2k into 1k. Okay, k cancel. Nothing but 4 by 2, 2 volts. Okay, this parallel resistor will become series resistance. 1 kilo ohm. This also 1 kilo ohm. Okay, this is a 2 kilo ohms. We need to find this VT. Directly let us write here. Okay, it seems like two resistor series. This is 2k and this 2k. Both are in series. Okay, then same current flows or voltage division rule. Directly we can apply the voltage division rule. Tell me the voltage division rule here. Voltage division rule, VTH. This is a 2 kilo ohm resistor. This is also 2 kilo ohm resistor. Voltage getting divided. Okay, equally 2k by 2k plus 2k into total voltage 2. Or this is 2 by 4k, nothing but 1 by 2 into 2. What is this value then? VTH equal to 1 volt. Okay, this VTH equal to 1 volt is the right answer. Option A is correct answer. Okay. Let's move on to next question. Okay, this question given from digital. Okay, it seems like a multiplex. The output function, output F. They're asking what is the output F of the digital circuit shown in figure. They're asking us to determine this one, right? This is from digital electronics. Okay, and what is the output equation of a 2 by 1 mux? If any 2 by 1 mux is given like this, if you know the selection line, okay, selection line. Okay, and you have two inputs I0 here, I1. Then for 2 by 1 mux, what is the output here? This S bar into I0 plus S into I1. When this selection line is low, this will be selected as an output. When the selection line is high, this input will be selected as an output. Okay. Let us calculate, let us assume this is y1 here. Okay, y1. What is the y1? This input low given as 1, input high connected to ground. Okay, when the selection line is low, connected to this 1. When selection line is high, connected to this low. Then this y1, okay, this y1 nothing but b bar into 1 plus b into 0. Anything into 0, 0. This is b bar. It's a y1. The output of this one is given as the input to the next one. Okay, the input for this one is B1. Right, input for this one is B1. What is the output of Y for the F or Y2? Okay, what is the Y2 or F here? This F equal to, again, it's a multiplexer. 2 by 1 mux. When this is low, this will be selected as an input, output. When this is high, this will be selected as an output. Okay, this is A bar into 1 plus A into B bar. That's all. Or this is A bar plus AB. A bar plus AB bar. If you simplify this one, we know this seems like this one complement of this one is available. Then output of this one nothing but simple this term plus this term. A bar plus B bar. This is the output Y. This is a MSQ question. Multiple select. MSQ. Okay, F equal to A bar plus B bar. Okay, F equal to A bar plus B bar. This is right. Similarly, you can also apply De Morgan's law. Okay. It's also can be written as AB bar, also equal to AB bar. It's option D also right. Both options B and D are correct. Both and D are correct. It's a MSQ question. Multiple select question. Right. Let's move on to next question. The logic circuit shown implement. Okay, they're asking this logic circuit shown implements dash functionality. They're given some 4 options here. This question also came from digital electronics. Okay, and here this is B. Okay, true output B input is available. B bar is available from this NOT gate output. Similarly, true output A is available here. This is A. Output of NOT gate will give the A bar. Okay. Okay, and if you notice here, these are the OR gate, NOR gate, NOR gate. Okay, And here this output is given as an input to this one. This is A bar available, this is a B bar available here. And for this one, this is a true input A and the complement output B bar is available. Then what is the output of the first NOR gate? Okay, NOR gate. This is A sum of the inputs complement whole bar. A bar plus B bar whole bar. And what is the output of this one? It's A plus B bar whole bar. A plus B bar whole bar. Simple. Or this is, if you can rewrite like A B bar whole bar, or this is nothing but AB. Okay, whatever the input applied here, nothing but AB. And if you want to simplify this one, you can write like a okay. If you want to simplify this, you can write like a bar into B bar whole bar or A bar B. Okay? A bar B. This is the input available. Then what is the output F? Okay, output F. This output F nothing but again NOR gate, NOR of AB comma A bar B. Okay? Or this is AB plus A bar B whole bar. And here if I take a B common, this is A plus A bar whole bar. And true literal and its complementary literal, okay, add up from 1. This is 1 whole bar. That what's the output here? It's B bar. Functionality F. What is the F here? So out of these options, D is the right answer. Simple question, straightforward. Be patient. Okay, don't commit any mistakes here. That's all. We can solve this. Let us move on to next question. This question came from digital electronics only. And, seems like a counter. Okay, they're asking which type of counter. Okay, A, B, C, D. Divide by 8 counter, divide by nothing but mod 8, mod 7, mod 5. Doesn't function as a counter. Okay, they're asking different types of counters. Okay. So here, no need to do everything here. Simply, okay, take the states. Take some states here. This output of, okay, Q0, Q1, Q2. Yeah, I'm writing the states here. Okay, this is Q0, Q1, Q2. Okay, let us assume initial conditions here. Let this be 0, 0, 0. Let us check. Let us give some clock pulse and let us check the states. So here, output of first stage is given as input of the next stage. Next, okay, this stage output is given as input to the next stage. And here, this output and this output will be given as D inputs here. This Q2, this Q1, this is NOR gate. Okay, but Q1 plus Q2 bar is given as input to D. Okay, D naught. Okay, nothing but this stage, okay, add them NOR, okay, NOR, okay, do the NOR operation for these two. NOR. Okay, what is 0 plus 0 whole bar? This is 1. If I give the pulse, okay, this will be transferred to the next stage. Okay, this will be transferred to the next stage, and NOR operation of these two, okay, will be come to the first stage. Okay, you notice here, this 0 will be transferred here. This 0 will be transferred here. This 1 will be coming over here. Okay, if I give another pulse, this 1 will be transferred here. This 0 will be transferred here. Okay, right. And okay, it says 0 NOR 0. 0 plus 0 whole bar, nothing but 1. Okay, that 1 will be coming. 0 plus 0 whole bar will be coming here. Right. In the next clock pulse, okay, this will be shifted here. This will be shifted here. Okay, and 0 plus 1 whole bar. Okay, 0 plus 1 whole bar, nothing but 0. Okay, 1 bar, but 0 will be coming here. This 0 will be coming. 0 plus 1. Okay, but 1 whole bar, but 0. In the next clock cycle, this 0, this 0, this 1 are shifted here, and 1 and 1, 1 plus 1, 1 bar 0 will be coming to here. Okay, and in next clock cycle, this 0 will be going to the next stage. This 0 will be going to the next stage. This 0 plus this NOR of 0 and 1. 0 plus 1, 1 bar, but 0 will be coming to the next stage. And if you notice here, the same thing getting repeated again. The same thing getting repeated. See here 0, 0, 0. First stage is 0, 0, 0. Next stage is 1, 0, 0. Next stage is 1, 1, 0. Next stage is 0, 1, 1. Next stage is 0, 0, 1. Okay. From here again it's getting repeated. 0, 0, 0. Again the same thing getting repeated. This becomes 1, 0, 0. This becomes 1, 1, 0. So on. Okay. How many different states are there? Different states. Okay. This is one different state, one different state, one different. Okay. 5 different states are there. 5 different states. 5 different states. Okay. Therefore, it's a modified one. Modified counter. Okay. Or divide by 5 counter. C is the right answer. Modified counter. Okay. Option C is the correct. Okay. Right. Let us move on to next question. If you notice here, A is given as 2 bits, A1, A0. B is given as 2 bits, B1, B0, or 2-bit unsigned binary numbers. If F equal to A1, A0, okay, function of, okay, all those 4 bits is a Boolean function such that F is 1 only when A is greater than B. Okay, F is 1 only when A is greater than B. Okay, if you see here, let us write the truth table first of all. You have the bits. Okay, this is A1, A0. This is B bit, B1, B0. Okay, you have 4 bits here. You will get a 16 combination, right? 16 combination. Right? They asking F. Okay, when A is greater than B. This is A bit here. This is the B bit. This is 16 combination. I can consider as 0, 0, 0, 0, 0, 0, 0, 0. Okay, wait. Let us see. See here, this can be 0, 0, this can be 0, 1, this can be 1, 0, this can be 1, 1. This is 4 combinations. The next stage, I can consider this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. The next stage, I can consider 1, 0, 1, 0, 1, 0, 1, 0. I'm keeping this as a constant. Let us vary this one 0, 1, 1, 0, 1, 1. The next stage, okay, this is 1, 0, 1, 1, 1, 1, 1, 1, 1. This becomes 0, 0, 0, 1, 1, 0, 1, 1. Okay. And here, notice here, 14. Okay, 16 combinations I got. You just, okay, for your sake, understanding purpose, what I am doing is let us deal them in decimal. Okay. This magnitude is 0, 0, 0, decimal. Okay. Decimal, I'm writing the values. This value is 1, 1, 1, 1, decimal. This value is 2, 2, 2, 2. This value is 3, 3, 3, 3. Okay. Here in decimal, this value is also tell me in decimals. Okay. This value is 0, this is 1, this is 2, this is 3. This is 0, this is 1, this is 2, this is 3. Okay. 0, 1, 2. Here also 0, 1, 2. Okay, you compare the values. This is magnitude is 0, this magnitude is 0. Okay, whether 0 greater than 0? No. Output is 0. 0 greater than 1? No. Okay, then this is not true. 0 greater than 2? No. 0, 0, not greater than 1, 0. Okay, this output is also 0. This magnitude is 0, this is 3. Okay, 0 greater than 3? No. Okay. Then, okay, here 1, this is 0. 1 greater than 0? Right. Output is true. 1 greater than 1? No. 1 greater than 2? No. 1 greater than 3? Similarly, tell me this combination. This is 2, this is 0. 1, 0. Let us compare whether it's greater or less, okay, or not compared to this one. 2 greater than 0? Yes, true. 2 greater than 1? Yes, true. 2 greater than 2? No. 2 greater than 3? Okay. Here, let us compare this and this. 3 greater than 0? Yes. 3 greater than 1? Yes. 3 greater than 2? Yes. 3 greater than 3? No. Okay. If I write them in the, okay, these are 4 bits are there. What are the different combinations for this one 4 bits? Notice here. This is 0, 0, 0, 0. Okay, this is 0. 0, 0, 0, 1. This is 1. Okay, 0, 0, 1, 0. This is 2. 0, 0, 1, 1. This is 3. 0, 1, 1, 0. Okay, this is 4. 0, 1, 0, 1. Okay, 5. This is 0, 1, 1, 0. Okay, 6. Similarly, 7. This is 8. This is 9. This is 10. This is 11, 12, 13, 14, 15. Okay. When you got high for this one, this one, this one, this one. Okay, this is f of a greater than b. Okay, or function of a1, a naught, b1, b naught for a greater than b. Okay, for a greater than b, we got when the output is high out of 16 combinations for 4, for 8, for 9, okay, for 12, for 13, 14. That's all. Okay. They're asking the answer in terms of sum of products. Okay. They're asking the answer in terms of sum of products. Let us try to simplify this one. 4, 8, 9. You got 4, 8, 12, 13, 14. Okay, this is 12, this is 13, this is 14. Okay. Let us draw the K map here. 4 variable K map. This is A1, A naught, B1, B naught. 4 variable K map. Let us try to simplify it. Let us draw the 4 variable K map and simplify this one. Okay, here this is 0, 0, 0, 1, 1, 1, and 0. 0, 0, 0, 1, 1, 1, 0. Okay. This is 0, 0, 0, 0, 0. This is 1. Okay, this is 3. This is 2. This is 4. This is 5. This is 7. This is 6. This is 8. This is 9. This is 10. Okay, this is 11. This is 12. This is 13. This is 14. This is 15. Okay, this is A1, A naught here. This is B1, B naught here. Let us take those values. And please tell me, okay, which combinations you got here? 4, this is high, 8, high, okay, 9, 12, this is 13, this is 14. Let us check whether any possibility of getting 16 rounding. No. 8, no. Then you have a quad here. Quad. 4. 4 you can round it up. Next, which thing you can round here? We can round this one. We can round this one. Right? 2. We can consider them as 2. Next, similarly, which thing you can round? You can consider this. Right? Okay. Let us write the output here. Let us write the output. Okay. For this 4 bits, tell me the for this quad, what is the tell me here. This here common is 1, 1. Therefore, A1, and here this 0, 0 common B1 bar. Okay. And if I take this one for this one, this is in this row 1, 1. Okay, this is A1, A naught, and here these two are common, right? 0, 0 common. Therefore, B naught bar. And if I go to this one, okay, if I go to this one, it is in this row B1 bar, B naught bar. Okay, in this column. Okay, B1 bar, B naught bar, and in these two, this A naught is common. Okay, therefore this is A naught. That's all. Therefore, what is the total functionality here for f of a greater than b? This is A1 B1 bar plus A1 A0 B0 bar plus B1 bar B0 bar A0. Okay, you choose the right option. Okay, here, right. It's A is the right answer. A1 B1 bar, A1 A0 B0 bar, A0 B1 bar B0 bar. Okay, B1 bar B0 bar. That's the right answer. Option is the right answer. Let's move on to next question here. Okay, an analog to digital converter with a resolution 0.1 volts. Okay, an analog to digital converter with a resolution 0.1 volts is given. Okay, converts the analog signal between 0 to 10 volts to an unassigned binary output. The minimum number of bits in integers in the output is they asking. Analog to digital converter with resolution. They given the resolution. What is the resolution they given? Resolution, it is given as 0.01 volt. Okay, resolution. Converts the digital. Okay, this converts the digital. Okay, digital to analog to digital, right? 0 volts to 10 volts. Okay, 0 volts to analog signal from 0 to 10 volts. Okay. Then here itself 0 to 10. What is the full scale output voltage? Full scale output FSO. Okay, output voltage FSO. FSV. Then full scale output voltage nothing but 10 minus 0. This is 10 volts. Full scale output voltage. What they're asking us to determine the minimum number of bits in integers in the output is. Okay. Right. Minimum number of bits. Actually, we know one thing. This is a full scale output. Okay. FSO or FSV. It's a full scale output equal to step size. Step size into number of steps. Step size into number of steps. Okay. And here resolution itself nothing but the step size. This step size given. Okay. And the number of steps. Okay. What is the, how many number of steps will be there? 2 power n minus 1. This is step size. Full scale output voltage given as 10. Resolution of step size given as 0.01. And the number of bits, if you know the number of bits in, then 2 power n minus 1. Okay. Therefore, this is 10 by 0.01. Okay. Equal to 2 power n minus 1. That itself implies 2 power n minus 1 equal to 1000. Okay. Or 2 power n equal to 1000. Then you this value n. Then in this n equal to log of 1001 base 2. Okay. What is this value? Calculator. If you take this calculator, do it 2.96578 something. Round off this value and the nearest integer you require. Therefore, answer is 10 bits is the right answer. 10 bits. 10 bits is the right answer. Okay. Here. 10 bits. Right answer. Let's move on to the next question. Okay. Right now, they're given the signal flow graph SFG. This question belongs to control systems. The signal flow graph SFG, okay, shown in figure, the expression for y of s by x of s is. Okay, if you notice this one. Okay. So here, how many forward paths are there? See how to find the transfer function in signal flow graph. P1 delta 1 plus P2 delta 2 divided by the delta. Okay. Delta. Simple. That's all. How to calculate delta? 1 minus, okay, number of non-touching loops. Okay. Next, plus number of two non-touching loops. Product will add the sum. Minus, okay, 3 non-touching loops will take. This is the way how to calculate delta. Here, if you observe here, how many forward paths? P1, P2, P3, so on. Okay. Plus so on. Divided by this is the total delta. Here, tell me how many paths. Therefore, this can be written as sigma pk delta k divided by delta. Okay. Delta, where k varying from 1 to so many. Okay. How many forward paths? Tell me how many forward paths are there? This is one. Directly we can go to y of s like this, from x of s to y of s. Okay, there another forward path is like this. We can go to this one. There are two forward paths. What are those two forward paths? This is one path. This is g1 of s. This is g2 of s. This is 2. Okay. This is x of s. This is y of s. Okay. And another forward path. This is another forward path. Okay. This is 2. This is g3 of s. This is g1. Timing I'm take okay g1 only instead of s. Okay. Okay, I have two forward paths. What is path 1? Okay, this path 1 nothing but product p1. Okay, g1 g2. What is p2 here? 2 into, okay, this is 2 into g1 g2. This is 2 into g1 g3. Okay, 2 into g1 of s, g2 of s. 2 into g1 of s, g3 of s. Okay, right. How many loops are there? Please identify the loops here. Okay, loops. How many loops are there? Tell me. Loops. Loops. How many loops are there? You consider the loops here. Okay, you got a loop like this. This is one loop. Okay. This is G2. This is minus 1. This is L1. L1. What is L1? Minus G2. Minus G2. Okay. Is there any possibility of another loop? Yes. Okay. This one is another loop. Okay. Another loop. From here, this is another loop. Okay. This is G3. This is minus 1. Then L2. What is this L2? Minus G3. Minus G3. Right, everyone? Here. Right. Okay. This is the forward path. For this forward path, without this forward path, this is the loop. Without this forward path, this is the loop here. Okay. Okay. I'm writing again. P1. What is P1 we got here? P1. Got 2G1, G2. 2G1, G2. P2. What is the P2 we got here? P2 we got here 2G1, G3. 2 times of G1, G3. What is the L1 we got here? L1. Okay, individual loops minus G3. What is L2 we got here? L2 okay, minus G2. Minus G2. Okay, right. Okay, notice here, these are the individual loops. P1. This is a path 1 we got here. We got this path 1 like this. This is 2, G1, this is G2. Path 2 we got like this. Okay, this is G1, this is G3, this is 2, right? P1 path, P2 path. Okay, if I calculate delta 1, okay, whether any without excluding this path, any chance of loops getting formed in this one? If I remove this G1, G2, G3, no. Okay, not possible. 1 minus 0. This is 1. If we calculate delta 2 for this one, if I exclude this second path, if I exclude this second path, any chance of loops? No, not possible. Therefore, this is 1 minus 0. Okay, this is also 1. Then what is the trans function? Okay, sigma pk delta k divided by delta. Okay, and this is here only two paths, delta 1, p1 delta 1, p2 delta 2 divided by delta. What is p1 here? This is 2 g1 g2 delta 1 1 p2 2 g1 g3 delta 2 also 1 divided by only single loops are formed here. Okay, non-touching loops. Okay, L1 is 2. Okay, minus this one. Single touching loops. No, 2 non-touching loops. No, 3 non-touching loops. So on. So therefore, what is this transfer function then? Got 2 g1 g2 plus 2g1 g3 divided by 1 plus g2 plus g3. Okay. Or if I write in a proper way, 2 into g1 of s, g2 of s plus 2 into g1 of s, g3 of s divided by 1 plus g2 of s, g3 of s. Okay. You choose the proper answer. 1 plus g1 of s 2 into g1 g2 2 into this is wrong. This is also wrong. This is also wrong. Okay, this is the correct answer. 2g1 g2 2g1 g3 divided 1 plus g2 g3. Okay, right. Okay, let's move on to next question. The transfer function of a system is, okay, they given the transfer function s plus 1, s plus 3 by s plus 5, s plus 7, s plus 9. The state space representation of system, the minimum number of state variables. Okay, here the state variables always number of state variables. Number of state variables, nothing but order of a system. Order of a system. Okay, order nothing but number of poles. How many number of poles here? Okay, this is 1, this is 2, this is 3. That's all. 3. That's finished. Let's move on to next question. Okay, the complex z equal to a plus jb by a minus ab, where a greater than b, 0, b greater than 0. Then what is the phase shift magnitude? They are given the options. So directly straightforward basic question here. What is the magnitude or modulus of z square root of, okay, modulus of a plus jb, okay, modulus of a plus jb by modulus of a minus jb. Okay, this is square root of a square plus b square divided by square root of a square plus b square. That's all. What is the magnitude? Getting cancelled 1. And what is the phase? Phase. If you ask the phase, okay, this a plus jb is in the a plus jb in the first quadrant. A plus jb. Okay. This a minus jb is in the fourth quadrant. Okay, a minus jb. What is this angle? This is tan inverse of b by a. What is angle? Minus tan inverse of b by a. Okay, this angle nothing but tan inverse of b by a. This angle nothing but tan inverse of minus b by a. Minus tan inverse of b by a. Okay, theta 1 divided by theta 2. Okay, nothing but theta 1 minus theta 2. Or this is tan inverse of b by a minus tan inverse of b by a. Okay, minus of minus, this becomes plus. This is 2 times of tan inverse of b by a. This is also MSQ type of question, MSQ multiple select question. Magnitude is 1, angle is 2 tan inverse of b by a. Magnitude is 1 is correct. Tan inverse of 2 tan inverse of b by a is correct. Okay, it's not 2 tan inverse of 2b by a. Okay, this is 2 into tan inverse of b by a. Both options B and D are correct. Okay. Let's move on to next question. The periodic function f of x with a period 2 is defined like this. Okay, some f of x they given. The Fourier series, okay, this portion belongs to signals and systems as well as mathematics. Okay. Contains, they're asking sine terms, cos terms, or sine cos 2 times, okay, cos n, cos sin n. They're asking like this. Okay, this question here you can solve by using simple. Okay, you learn them something like odd symmetry, even symmetry, halfway symmetry, like. First of all, let us plot this one. What is this given here? Okay, it seems like first function. If I take the function, how it seems like, if I take minus common, this is x plus 1. First term, if I take minus common, this is x minus 1. Okay, this is the limits 1 less than x less than equal to 0. This is the limits x less than equal to 0 less than x less than equal to 1. Okay, this is a minus, is there minus x, actually minus x. If I take f of x with respect to x, okay, everyone tell me one thing. Okay, what is f of x? How that f of x look like? Okay. F of x is minus x. If I draw this one, minus x means this is the minus x. Slope is negative passing through. Okay, minus 1 passing through origin. Okay, next this is x minus of x minus when compared to this one, if I want to plot this one, minus of x minus 1. Okay. When compared to this signal is delayed by 1 unit. Okay. This is minus x only. Okay. This signal is delayed by 1 unit. Delayed signal. Delayed. Okay, if I want to plot this one, minus x only, this is minus of x plus 1. What is x plus 1? This signal is advanced by 1 unit. Advanced by 1 unit. Okay, 1 unit advanced. This is delayed by 1 unit. Okay, this is advanced by 1 unit when compared to origin here. Right. This is the final signal. And notice here. What is this f of x, total f of x? I consider some signal minus x. Okay, I plotted with respect to x. When signal is delayed, when the signal is advanced, okay, this is the thing. Right now, let us plot the given signal. What is the given signal? F of x equal to minus of x plus 1 between the limits minus 1 to 0. Minus 1 to 0. This is signal. Between 0 to 1, okay, this is act as a minus of x minus 1. Okay, everyone notice here. Between the limits minus 1 to 0, minus 1 to 0, this is the signal. Between 0 to 1, this is the signal. 0 to 1, this is the signal. That's all. You plot this one, this is the f of x. Okay. Plotting this f of x is one half job done. Okay. Right now, let us check whether the given signal is even function or odd function. Okay. Right now, this is f of x. What I'm trying to do is, let us try to plot the f of minus x. Minus x. Okay. Whatever the part, this part, positive intervals of x will fall under negative intervals of x. Okay. This is a signal. This part. Okay. Just folding with respect to vertical axis. Similarly, this part will come for this. Okay. Folding with respect to vertical axis. This is the value from plus 1. Okay. And right now, whether these two are same, no, f of x not equal to f of minus x, therefore not even function. Now what we'll do is, let this function multiplied by minus 1. Okay, multiplied by minus 1, the entire function, what I'm trying to do is, let us multiply by minus 1, minus of f of minus x with respect to x. Okay, and whatever the signal here, that signal falling here, whatever signal here, okay, negative signal will comes for positive. This is 1, this is minus 1. Okay, this value is here 1, okay, this is minus 1, this value 1. And if you notice here, this signal and this signal both are same. F of x equal to minus of f of minus x. Then this type of signals are called odd signals. Odd signals. Okay. When the signal is only having the odd, okay, odd, only sign terms will be present in the circuit. No cos terms. Okay. Answer B, C are wrong answers. Okay. And both sine and cos terms will be having present in the circuit is also wrong. Okay. Only, sir, see here, all cos terms are absent in the system. Only sine terms will be there. Okay. Only sine terms. Only sine terms are present. Therefore, answer A is the right answer. Everyone, answer A is the right answer. See here, again, if you want to check the halfway symmetry, since they not asked only even terms or odd terms are present, no need here. No need to check the halfway symmetry. Just check whether the signal given signal is even signal or odd signal. Given signal is odd signal. Therefore, all the cos terms are absent. Therefore, only it consider only sine terms. That's okay. Let's move on to next question. Therefore, answer only sine terms. That's it. Option A is the correct answer. Okay. A unity gain negative feedback control system has a loop gain given by L of S. Okay, it is L of S given as 6 by S into S minus 5. The closed loop system is, okay, they're asking about the closed loop system. Actually, it seems like some system is the open loop gain L of S, right? It's the output. Okay, it's a L of S negative feedback system. This is plus here, this is minus here, right? And this gain, this feedback is a unity gain. Then what is a closed loop transfer function? Closed loop transfer function given system nothing but g of s by 1 plus g of s into h of s. G of s by 1 plus g of s into h of s. And here h of s nothing but 1. Okay, this is g of s nothing but L of s. 1 plus L of s into 1. Okay, what is L of s? 6 by s into s minus 5 divided by 1 plus 6 by s into s minus 5. Or this is 6 by, okay, this is s into s minus 5 plus 6, or this is 6 by, okay, s square minus 5s plus 6. This is a closed loop transform. Then what is the characteristic equation? Okay, or this closed loop transfer function we got like here 6 by s square minus 5s plus 6. Okay. Or I can write like a roots s minus 3, s minus 2. Okay. Then closed loop transfer function poles. If I draw this S plane, poles. It's a sigma plane. This is j omega plane. I got the poles at 2, poles at 3. Okay, these poles are lying in the right half of the S plane. If poles right on the lying in the right half of the S plane, system is unstable. Unstable. If you find the response here, okay, suppose okay, you will get partial fractions. If I write partial fractions, notice here. Okay, a by s minus 2 plus b by s minus 3. Okay, I have evaluated closed loop transformation. We got the values of a and b. Then, okay, what is the response? Inverse Laplace transform. If I apply inverse Laplace response, okay, response for this one, you will get e power minus 2t plus 2t. This you will get e power plus 3t into u of t. In control systems, we will see the causal systems, okay, for the response for t greater than 0. And if I plot this one, it's like a growing function. If I plot this one, it's also like a growing function. For a bounded input, if you are not getting bounded output, then system is unstable. Okay, or directly from here, all the poles are lying in the left half of this plane. System is unstable. Okay, unstable system. So B, D, C are wrong answer. Okay, it's an unstable system. And this signal lying only between 0 to infinity only. All these are causal systems. Okay, it's a causal unstable system. Is the right answer. Causal. Why this is causal? This response is here for all time t greater than equal to 0. That's why system is causal. That's why answer is causal and unstable is right answer. Next, okay, the signal x of t is given by t minus 1 whole square into u of t minus 1, where u of t is the unit step. Okay, has a Laplace transform x of s. They're asking what is the x of 1. Okay. Here, what? Let us take one thing here. Let us take x1 of t. Okay, some signal I am taking t square into u of t. Some signal t square into u of t. Then for this signal, if I apply Laplace transform, okay, then what is x1 of s? Tell me. This x1 of s. Okay, this is 2 by s cube. We will get a t square. That's all. 2 by s cube. And if you compare this x1 of t here, this x of t, how this x of t is defined? X1 of t minus 1. Okay, t, wherever you have t, this is a t minus 1. Wherever you have t, t minus 1. Okay. And we have studied Laplace f of t. Okay, Laplace, suppose f of s. Then if this f of t is delayed by t naught, okay, then what is the Laplace transform? E power s t naught minus s t naught into f of s. Same way, then what is the Laplace transform of this one? X of t, Laplace transform of x of t. Okay, this is x of s. This can be written as, okay, e power minus s into 1 x1 of s. Okay, or this is e power minus s into x1 of n by 2 by s cube. This is x of s. Okay, in the question they are asking us what is the value of x of 1. Wherever we have s, replace by 1. Then what is x of 1? E power minus 1, 2 by 1 cube, or this is 2 by e. That's your x of 1. That's all. Okay, here in this question they given the options here. I'm showing the options. Please select those options. Option A given as 1 by e, option B given as 2 by e, option C given as 2 into e, option D, okay, it's given as e square. Okay, answer is 2 by e is the right answer. Let's move on to next question. The output of a system y of t is related to its input x of t by following relations: y of t equal to x of t into sine of 2 pi t. Then they are telling, okay, asking whether system is linear, non-linear, okay, time variant, time invariant. If you see these options, okay, if you see this y of t, okay, for a system x of t giving to a system, and what's the response for that system y of t? We got x of t into sine 2 pi t. Okay, if you want to check for linearity, weighted sum of inputs, if you're getting weighted sum of outputs, then the system is linear. Here, if I give a1 x1 of t plus a2 x2 of t, okay, if I am giving here a1 x1 of t plus a2 x2 of t, then what's the output you're getting here? a1 x1 of t plus a2 x2 of t into sine 2 pi t. Okay, this is the output, weighted sum of inputs. Weighted sum of inputs. Weighted sum of inputs if I give, okay, you got like this. If I give weighted sum of outputs, okay, weighted sum of outputs, if I'm checking a1 y1 of t plus a2 y2 of t, or this is a1 y1 of t. What is y1 of t? x1 of t sine 2 pi t. Okay, this is a2, okay, x2 of t 2 pi t sine 2 pi t, or this seems like a1 x1 of t plus a2 x2 of t sine of 2 pi t, okay, sine 2. This is a weighted sum of inputs giving the weighted sum of outputs. Weighted sum of inputs giving the weighted sum of outputs. Okay, therefore system is linear system. Linear system is a linear system. Okay, and here let us check the time varying or time invariant. Given system y of t is x of t into sine of 2 pi t. Okay, everyone, for this system, okay, how to check whether the system is time varying or time invariant? To delay the system, delay the input. Okay, delay the input. If I delay the input, you are getting x of t minus tau. Then what is the corresponding output then? Output, but x of t minus tau into sine of 2 pi t. Okay, for delayed input, you got the response like this. Okay, let us check delay the output. Delay the output. Y of t minus tau. Okay, by tau units. Okay, this is you have x of t like this, function of t, x of t into sine 2 pi t. Let us delay the entire thing. Wherever you find t, replace it by t minus tau. This is x of t minus tau, sine of 2 by t is there, t minus tau. Okay. Now check it out whether this one and this one both are same. Whether this one and this one both are same. No. Here only input is delayed. Here this wherever you have t, everything is delayed. Okay. Both are not same. Okay. Then it's a time varying function. Time varying. Okay. It's not time invariant. It's a time varying. Okay. That's why its system is a linear time varying system. Option D is the right answer. Option D is the right answer. Let's move on to next question. Determine the transfer function of an LDA system described by the differential equation. Okay, they're given some differential equation. Okay, right. They're asking the transfer function. See here, if you notice this system, okay. Suppose if I'm talking about x of t into u of t, some signal x of t is there, some signal x of t is there, some signal. This is the u of t signal. If I multiply these two signals, I'll get x of t into u of t. This is u of t, this x of t. If I multiply these signals, I'll get some signal like this from 0 to. And if I delay this entire signal, I will get the by 3 units. This entire signal shifts by 3 units. X of t minus 3, u of t minus 3, everyone. Right. And we know one thing, if x of t Laplace transform is x of s, y of t Laplace transform is y of s, then d by dt of y of t, d by dt of y of t will give s into y of s, neglecting the initial conditions. Okay? Right. And similarly, x of t minus t naught will give e power minus st naught into x of s. Okay? Right. Let us take this differential equation. Let us apply Laplace transform on both sides. Tell me. If you apply Laplace transform on this one, this becomes s into y of s plus y of s. This is entire signal x of t into u of t, also x of t only. Okay, it makes the signal causal. Okay, it makes the signal right-sided causal. X of t, x of s, then x of t into u of t also, x of t in the right-sided signal. Okay, makes the signal causal. Then what is the Laplace transform of this one? E power minus s into 3 x of s. Therefore, this if I take y of s common here, this is s plus 1 equal to e power minus 3s to x of s. Then what is y of s by x of s then? E power minus 3s by s plus 1. Okay. You choose the right answer of the given options. Okay, option A, e power minus 3s by s plus 1, right. This is s by 3, wrong. Okay, this is also e power s by the wrong. E power minus 3 only given. Okay, by s plus 3, wrong answer. Option A is the correct answer. Option A is correct answer. Let's move on to next question. A signal x of t is band limited between 100 Hz and 200 Hz. A signal y of t is related to x of t as follows. Okay. Y of t is given as x of 2t minus 5. Yeah, this is a question based only on the simple concept of properties. Okay. So here they told x of t is band limited. Okay. Suppose this some signal x of t is there. If I apply the Fourier transform, I got x of omega or x of f with respect to f. Okay. Band limited. Okay. This is band limited. Suppose something like this. 100 Hz to 200 Hz. 100 Hz to 200. And we required the properties to solve this one. So here y of t equal to x of 2t minus 5. Okay. This is scaling property. Scaling. When scale is x of at, when x of a into t, okay, this is when a greater than 1, okay, this is compressed. In time domain it will compresses. When a less than 1 it expands. Okay. Since 2t 2 greater than 1, okay, this is a in time domain compression. Time domain compression. Okay. And one thing here, suppose x of at is there, if I apply the Fourier transform, will become 1 by mod a x of omega by a or f by a. Okay, it see here compression in time domain, nothing but expansion in frequency domain. Suppose the signal x of 2t is there, this is 1 by 2 x of, okay, this omega by 2. Here this becomes, here if it is compression here, compression, and becomes expansion here, expansion. Compression by 2, nothing but expansion by 2. Here, same way, if the given signal y of t equal to x of 2t minus 5, okay, delay here, you will get that factor e power minus s into some factor. Magnitude of that e power minus s into that, nothing but 1 only. Right. Okay, this right now x of 2t compression in time domain. Okay, and in a frequency domain, if I plot this f of y with y of f with respect to f, this will get expanded by 2. 100 into 2, this becomes 200. 200 into 2, this becomes 400. Okay, then you can answer this question by seeing the options. Tell me here, what is the answer? Y of t is mad band limited. Wrong answer. Y of t is band limited only between 200 to 400. Y of t is band limited between 50 and 100. Wrong answer. Y of t is limited between 100 to 200. Same like this. Wrong answer. Y of t is limited between 200 to 400. Right answer. Clear everyone? Following? Right? Very good. Therefore, answer y of t is band limited between 200 to 400. Right answer. Okay. Here, this also belongs to signals and systems. Okay. Just here, consider the transfer function HC of S. This is given as 1 by S plus 1 into S plus 3. Bilinear transfer with a sampling period of 0.1 seconds is to obtain the discrete time transfer function. Okay. HD of Z. Then what is HD of Z? Simple thing here, nothing is there. Just in place of S, we are going to substitute in terms of Z. What is that factor we are going to place in terms of Z? What is that value of S? Okay. This is a bilinear transfer. Okay. What is this bilinear transfer? Bilinear transfer. Okay. Bilinear transfer. What is the given? They given HC of S, some function 1 by S plus 1 into S plus 3. And they given the sampling, okay, period as 0.1 S, 0.1 seconds. This bilinear transfer function in place of S, what will place 2 by that sampling period to 1 minus Z inverse by 1 plus Z inverse. That's all finished. And here this S equal to sampling period 2 by 0.1, okay, into 1 minus Z inverse by 1 plus Z inverse. This is nothing but 20 into, in place of S, wherever you find S, you have to replace by 20 into 1 minus Z inverse by 1 plus Z inverse. Everyone. Given function, what is this function given HC of S? This HC of S given as 1 by S plus 1 into S plus 3. If you want to apply the bilinear transfer, okay, bilinear transfer, you replace S by 20 into 1 minus Z inverse divided by 1 plus Z inverse. Okay. So Z transform the given transfer function. So Z transform of the given transfer function. Given transfer function is HC of S. Okay. This HD of Z. What is this HD of Z here? 1 by S plus 1 into S plus 3. Wherever you have a S, you have to replace by 20 into 1 minus Z power minus 1 by 1 plus Z power minus 1. Okay. Or this is 1 by 20 into 1 minus Z inverse, 1 plus Z inverse plus 1 to 20 into 1 minus Z inverse divided by 1 plus Z inverse plus 3. Plus 3. Okay. Therefore, what is this HD of Z? This HD of Z equal to 1 divided by, right? Let us rearrange these terms here. 20 into 1 minus Z inverse plus 1 plus Z inverse divided by 1 plus Z inverse. And here 20 into 1 minus Z inverse plus 3 into 1 plus Z inverse divided by 1 plus Z. Okay. Or this HD of Z. HD of Z equal to what is here? Denominator, you have 1 plus Z inverse, 1 plus Z inverse. If you go to numerator, it becomes multiplication. Here 20 minus 20 into Z inverse plus 1 plus 20, okay, plus Z inverse. Second function, 20 minus 20 into Z inverse plus 3 into Z inverse. Okay. Or HD of Z. You take HD of Z, this is numerator 1 plus Z inverse whole square divided by denominator. This is 20 plus 1, 21 minus 20 plus 1 minus 19 Z inverse. Second term, 20 plus 3, this is 23 minus 20 plus 3. Okay, it becomes minus 17 Z inverse. That's all, finished. You choose the right option from these 4 options. For numerator, you have 1 plus Z inverse. Okay, 1 plus Z inverse. Okay, 1 plus Z inverse whole square. Denominator, you have 21 minus 19. 21 minus 19. Okay, 21 minus 19. Either C or D. 21 minus 19 Z inverse. And you have a 23 minus 17. 23 minus 17 is right answer. This is not this well. Okay, right. Therefore, option D is the right answer for the given question. Very good. Okay, this question given from analog circuits. Okay, in the circuit shown R1 equal to 100K. Okay, R2 equal to 1 kilo. If the base to the emitter voltage of NP and BJT is 0.7 volts, then the collector to emitter voltage is 5.2 volts. Then the collector gain, current gain they are asking. So here they given the R1 100K, 100 kilo. R2 given as 1 kilo. Okay. If the base to emitter voltage, nothing but this voltage given as 0.7 volt, base to emitter voltage. And the collector to emitter voltage. Okay, this is the collector terminal, this is the emitter terminal, this collector to VCE, okay, given as 5.2 volts. This is given as 5.2 volts. 5.2 volts. 5.2. This VBE given as 0.7 volts. This VC is given as 5.2. Then the collector gain, current gain beta, they are asking, what is this beta? Here, actually here, this current is nothing but IE current. Current flowing into the base, nothing but IB current. IB current. And this is the collector current. This current, if you ask me, IB plus IC, but your IE current is IE current. So here this voltage 5.2 volts with respect to ground. This voltage 0.7 with respect to ground, or this voltage nothing but 0.7 volts. This voltage is 5.2 volts. Yes or no? 5.2 volts. Now this current IB I can define starting voltage minus ending voltage by total distance. 5.2 minus 0.7 divided by resistance R1. This is 5.2 minus 0.7, nothing but 4.5 divided by 100K. What is value? 4.5 divided by 10 power 5, or this is 45 by 10 power 6. This is 45 microampere. That's the IB. And if I apply KVL for this outer loop, if I apply KVL, let us apply KVL for this outer loop. KVL. If you apply KVL, okay, minus 12 plus IE into R2 plus VCE equal to 0. That's all. Minus 12. Okay, this is actually source connected like plus minus 12 volts. Minus 12 plus IE into R2 plus VCE equals 0. R2 they given that value. Okay, minus 12 plus IE into R2 given as 1 kilo plus VCE 5.2 equal to 0. Then what is this IE? IE into 1 kilo equal to 12 minus 5.2. Or this IE equal to 6.8. 6.8 volts. Then this IE divided by 1 kilo. Or this IE we got as a 6.8 milliamperes. Okay, but they are asking beta. Okay, since IE nothing but IB plus IC. Okay, this is IB plus beta times of IB. Okay, or this is 1 plus beta times of IB. This IE current. IE current. Okay, this IE current nothing but beta times. Therefore, not here. This IE we got as a 6.8 milliamperes. Okay, this is 1 plus beta into IB, but 6.8 milli. Then 1 plus beta, this is 6.8 by IB. What is IB? We found out here 6.8 milli by 45 micro. Okay. Take the calculator. What is 6.8 by 45 micro? 151.111. You'll get. So this is 1 plus beta. Then what's the value of beta then? It's beta equal to 150.111, nothing but 150. 150. Say NET question. Data type question. 150 is the right answer. That's all. Completed, everyone? Let's move on to next question. Okay, they given a Zener diode. Okay, a diagram was missing here. Okay. This is the diagram they given. It's a Zener diode. Okay. It's input voltage. It's a load resistance. RL. This is Zener diode. Reverse bias. It's a regulator. Okay, this is a okay question here. If you notice the question, they given this is a 1200 ohms. This is your 16 volts. 16 volts. A Zener diode is used as a 4 volts regulator. Okay, this is a 4 volts breakdown voltage. Given that the diode requires a minimum current, diode minimum current 4 milliamps from this one, IZ minima. Okay, this IZ minima. What is IZ minima? They given us 4 milliamperes for regulation. The maximum current in milliamperes permitted to flow through load. They asking. Okay. Right, I'm again repeating the same diagram here, just modifying the diagram. Here, this is RL, 16 volts plus minus, this is 1200 ohms. This is a VZ, 4 volts given. Okay. IZ minimum, they given 4 milliamp. Right, here itself, we can conclude something like this. Here, if I'm assuming this is a ground, okay, this voltage, what is voltage VZ itself? VZ nothing but 4 volts. Okay. Can you please tell me what's the current I flowing here? What is I flowing? This side voltage, okay. This side voltage 16 volts. This side voltage right now 4 volts. Then what's the current I flowing here? This is 1200 ohms. Therefore, this current I is supplied by source nothing but starting voltage minus ending voltage by total resistance according to Ohm's law. Or this is 12 by 1200, nothing but 1 by 100. Or let us multiply 10 numerator, denominator. Okay, we got this 10 by 1000. 1000 in the denominator is nothing but kilo. When it goes to numerator, it becomes milli. Okay, this is 10 milliamperes. This is 10 milli. Okay, 10 milliamperes. Okay, notice here. When this current, okay, everyone notice one point here. Everyone notice this point. When this here, this current supply by source is always constant. Okay, the 10 milliamperes is constant. When this diode current becomes minima, this load current becomes maxima. Okay, that I or vice versa. When this diode current maxima, this load current becomes minima. This I, right now when this diode current is minima, IZ minima, its load current will become maxima. Maxima. Okay, that's all. Therefore, what is IL maxima? This is I minus IZ minima. Okay, what is the I value given? I we got like a 10 milli. What is IZ minima given in the question? 4 milli. The answer here 6 milliamperes is the right answer. 6 milliamperes. Here it's a very standard question. Regulator, Zener diode, competitive exams, very important. Straightforward question given here. 6 milliamperes. Okay. So here a question given on op-amp. An op-amp has a gain of 10 power 4. Okay, it's not an ideal op-amp. Okay, they given 10 power 4 ampere, 10 power 4 feet. And an input impedance, okay, Ra given as 10 mega ohms, and the output impedance R0 they given 100 ohms. The op-amp uses unity gain feedback configuration voltage buffer. Okay, okay, something like this. Okay, it's a unity gain voltage buff. The closed loop output impedance of op-amp in milliohms is, okay. They given this open loop output impedance, they asking the closed loop output impedance. Okay, closed loop output impedance. Yeah. What is the relation between open loop impedance and closed loop impedance? Okay, this is nothing but R naught by 1 plus A beta. And here this data is not required here. Okay, redundant data not required. Okay, here this open loop op amp input output impedance is given as 100. This is 1 plus gain is given as 10 power 4 beta. It's a unity gain feedback beta equal to 1. For this question, beta equal to 1. Or this is 1. Okay, this is 100 by 1 plus 10 power 4. 10,000 plus 1. Okay, nearly you can write as a 1,100 by 10 power 4. Okay, or this is 1 by 100. Question they're asking us to determine the output impedance in milliohms. Okay, this closed loop output impedance, but write 10 by 1000, multiplying 10 in the numerator denominator, or this can be written as 10 milliohms is the right answer. Answer 10 is the right answer for the given question. 10. Since they ask the answer in a milli, okay, answer 10 is the right answer. 10 milliohms is the right answer. Okay, next question. Let us move on to next question. The circuit is driven by a sinusoidal input voltage V in, resulting in the output voltage V out. Okay, the frequency in kilohertz at which the voltage gain is 0 dB. Okay, the frequency at which voltage gain is 0 dB. Yes, 0 dB. Here, see in dB, 0 means normal value is 1. Okay, 20 log of 1, nothing but 0. Nothing but where the frequency at which the voltage gain is becoming 1 unity gain or 0 dB. They are asking that frequency. Okay, right. Here, actually, see here, this is not a inductor, this is a resistor here given. This is a resistor. Okay, 10 kilo ohms resistor is given. Actually, a capacitor, resistor, okay, it's an ideal inductor, but this capacitor parallel with a resistor and a resistor here will become a practical inductor. It's a practical inductor. Okay, it's a practical inductor. It's a capacitor, resistor, combination of the practical capacitor. Okay, and this is a resistor. It becomes a practical inductor. And here it seems to be something like this. Okay, so some impedance. Okay, this is minus plus. Attaching also some impedance here. Okay. This is your Z1, something like this Z2. Okay, and here input given to the inverting terminal, and your non-inverting terminal is grounded. Okay. It's an inverting amplifier. Inverting amplifier. What is the output or gain? Okay, right. It's a practical inductor. It's just behaves like a your integrator only. Integrator. Right. Okay. Here, if f equal to 0, okay, everyone. If f equal to 0, frequency is 0. What happens if frequency is 0? In this one, if frequency is 0 here, this is a capacitor 1 by j omega c. This becomes infinity ohms, nothing but open. Okay, then that gain is called a DC gain. Okay, suppose if f equal to 0, then capacitor behavior, difference of capacitor 1 by j omega c, nothing but this becomes infinity 1 by 0. Okay, open. The gain here, then it seems like this. This is minus, this is plus. Okay, this is 10k. No capacitor right now. This is 100k. This is V now. Okay, you have an input here. Okay, this is 100k. Then this gain, whatever the gain, we are getting nothing but DC gain. DC gain. And you take the minus R2 by RF by R. This is forward resistance, feedback resistance by input resistance. Okay. This is magnitude I'm talking 100k by 10k. This value nothing but DC gain for the given 40. And here it acts as a practical inductor. Okay, it's a low pass filter. Okay, it's a low pass filter. It's a practical inductor here. This is a capacitor, this is a resistor. It acts as a low pass filter or integrator. And how the filter characteristics will be something like this. Filter characteristics will be like this. Okay, minus 20 dB, 20 dB. Okay, it's decreases like this, 0 dB. Okay, the circuit is driven by sinusoidal input voltage Vin, resulting in output voltage Vout. The frequency at which voltage gain is 0 dB. Okay, the DC gain for this one is nothing but your 10. Okay, right. Here, notice here, if this is Z2, this is Z1. Okay, what's the gain for this one? Gain. Okay, if you're talking about the gain function or H of, okay, what is this one? V naught by Vi. Okay, this is minus Z2 by Z1. Gain. Okay, this is gain. Or what is the Z2? These two are in parallel. Okay, this R2 parallel with 1 by S into C. And let us assume this is R1, this is R2 here. Okay. R2, this is suppose C. Right, divided by Z1. What is Z1? R1. This is R2 into 1 by SC divided by R2 plus 1 by SC divided by R1. Okay. R2 into, right. Or if you want to rearrange, this also can be written as R2 by 1 plus SCR2 divided by R1. R2 divided by 1 plus, or this is can be written as R2 by R1 divided by 1 plus S into CR2. There is a minus sign. I'm repeating that one. Therefore, this gain I'm representing by H of something. Okay, we got minus R2 by R1 divided by 1 plus S into C into S into C into R2. Okay, right? Simple, nothing, finished. H of J. Okay, right now we written everything in S domain. Right, what is this one? What is this value? What is the value of R2 given? R2 given as 100k, R1 given as 10k. R2 given as 100k, R1 given as 10k. Okay. What's the value of C given? C given as 1 nanofarad. 1 nanofarad. Okay, here, what is this H of S right now? This H of S nothing minus R2 by R1 up to 100k by 10k, nothing but 10 divided by 1 plus S into. What is C into R2? Tell me. C is a 1 nano. 1 nano. R2 nothing but 100k. 100 into 10 cube. This is 10 power minus 9, 10 power 5, 10 power minus 4. Okay. This is 10 power minus 4. We got like this. Right. Therefore, this is minus 10 by 1 plus S by 10 power 4. This is H of S. Or what is H of J omega? Wherever we have S replaced by omega, minus 10 by 1 plus J omega by 10 power 4. Let us calculate the magnitude of H of J omega. Magnitude of H of J omega, but magnitude of minus 10 by 1 plus J into omega by 10 power 4. Okay. Then here magnitude of H of J omega. This magnitude of H of J omega nothing but 10 by square root of 1 plus omega square 10 power 4 whole square. Omega by 10 power 4 whole square. And here in the question they given 0 dB. Voltage gain becoming 0 dB. Okay. This is the voltage gain. Voltage gain becoming 0 dB or 1. Okay. 0 dB or normal magnitude is 1. Okay. Let us substitute when this becoming 1. That's all. The corresponding frequency nothing but here 0 dB frequency. 1 plus omega by 10 power 4 whole square. Okay. is the square root of 1 plus omega by 10 power 4 whole square equal to 10. Squaring on both sides, this is 1 by 10 power 4 whole square equal to 10 square. Okay. Or this is omega by 10 power 4 whole square equal to 100 minus 1, 99. Okay. Or omega by 10 power 4 equals square root of 99. Okay, take the calculator. This omega equals square root of, okay, it's 10 power 4 into square root of 99 here. Since they're asking frequency in okay, kilohertz, they're asking the frequency in kilohertz, nothing but f only they're asking, f. Therefore 2 pi f equal to 10 power 4 into square root of 99. Okay, then what is the f here? Let us square root of 99 into 10 power 4 divided by 2 pi, or this is f equal to 2 pi 99 into 10 divided by 2 pi into 10, so many kilohertz. Okay, calculator, take this value square root of 10 root 99 divided by 2 pi. Calculator, tell me what is value. This is 15.83 kilohertz you'll get. It's a frequency. 15.83 kilohertz here. That's all. Very good, everyone. Next, let's move on to next question here. The circuit shown, enhancement N-channel MOSFET is biased in saturation region with transconductance GM. The channel length modulation is ignored. This is also straightforward, easy question only. What they're asking us to determine, if the channel length modulation is ignored, then the small signal impedance looking into the P naught. Okay, if you look into P naught, what is the small signal impedance? Nothing but R naught they're asking. What's the output resistance? Okay, output resistance look into this R naught. That's all. Okay, this is gate is grounded. Okay, this is a common, actually here for calculating output impedance we'll deactivate the independent sources present in the network. Okay, simple, let us replace this configuration this MOSFET by its small signal model. Okay, gate, no voltage is connected here. This is a gate grounded. Okay, you have a source connected to RS here. Okay, next here you have a GM into VGS, small signal model. If you apply here, where VGS is the voltage between this one, gate and source, and if you, and channel length modulation is neglected with nothing but no R naught resistor, and you have a RL resistor from here to here. Okay, RL. Usually, if you have channel length modulation, this output resistance R naught given by 1 plus lambda into VDS. Okay, and lambda equal to 0, then R naught equal to infinity. Okay, and no resistance, infinite resistance parallel to GM to VGS. That's all. What they're asking us to determine output resistance looking into this one. Okay, and what is the technique we used to follow? Have a DC source. Okay, connect a voltage source V, which is injecting current I. Take the ratio V by I, will give the R naught. It is R naught nothing but V by ratio. That's all. Here also same thing we are going to follow. Okay, let us connect a voltage source V, which is injecting current I. Take the ratio V by, will give the R naught. Everyone, that's all. That's all. Okay, and here if you notice here, this current and no current flowing here, 0 amperes open terminals, this current. Okay, and this is the current, nothing but this I plus GM into VGS is the current flowing here. I plus GM VGS is the current flowing. I plus GM into VGS is the current flowing. Okay, and here this V, this RS and V are parallel. This V equal to Ohm's law. If you apply Ohm's law, voltage into current. Okay, resistance into current is I plus GM VGS into RS will give that V. Okay, that's all. And here one thing, everyone, I'm taking this part of the circuit, I'm showing again. We got something like this. Okay, this is V. Right now these are parallel, this are voltage also V itself. Okay, this is VGS. This is grounded. Okay, this is also grounded. If I apply KVL here, KVL, then plus VGS plus V equal to 0, or this VGS equal to minus V. Okay, Vj is equal to minus V. Let this be 1, let this be 2. Let us substitute 2 in 1, 2 in. Then this V equal to I plus Gm into Vjs. What is Vjs? Minus V into Rs. Or this V equal to I into Rs minus Gm Rs into V. Let us subtract the terms containing V here. Let us separate the terms containing V here. Okay, V into V plus Gm Rs into V equal to Rs. V into 1 plus Gm Rs equal to I into Rs. Then what is V by ratio? This V by ratio equal to Rs by 1 plus Gm into Rs. That's all. Or we can do, let us divide by Gm denominator. Then this becomes 1 by Gm plus Rs. It seems like something like R1 R2 by R1 plus R2, nothing but R1 parallel to R2. Therefore, this is the output resistance R0, R0. How it seems to be, this Rs parallel with 1 by G. That's the answer for the given. Okay, if I choose this thing, the option B is the right answer. Option B is the right answer. Let's move on to next question here. Okay, a 1 kilohertz sine wave generator having an internal resistance of 50 ohms generates an open circuit voltage of 10 volts peak to peak when a capacitor is connected across the output terminals. The voltage drops to 8 volts when the capacitor, okay, then the capacitance of the capacitor in microfarads rounded up to. Okay, notice here, this is a 1 kilohertz sine wave, okay, input Vin, and have an internal resistance of 50 ohms, okay, and okay, they're telling here open. When this is open, what is the open circuit voltage here? It shows a 10 volts peak to peak. Nothing but this input voltage they given like this. And here, when this connected to a capacitor here, okay, what is the voltage here? We are getting 8 volts peak to peak, like this. Okay. Suppose if I assume V in and right now source at 1 kilohertz, okay, directly here open, but no current flows. Then this V in itself nothing but 10 volts peak to peak from the first diagram. When this is V in, okay, this is R, this is 1 by C farads, okay, capacitor, 1 by Cs, 1 by Cs, okay. Okay, this is 1 by Cs. Second. Okay, sorry. These are things we have discussed up to now. Okay, and this this is 1 by S into C ohms. Okay. Now tell me, what is this V out right now? This V out. Actually, this V out voltage division rule we can apply. Okay. Suppose this is V out. What is the voltage division rule? That impedance 1 by S into C divided by total impedance 1 by S into C into total voltage V, right? Or, or, or you can write, suppose the impedance you know as minus J XC ohms. Okay, or this also can be written as minus J XC by R minus J XC into V. Okay, this is your V naught. You got this V naught as minus J XC by R minus J XC into V. They're given 8 volts peak to peak. Okay, magnitude they are talking. What's the magnitude of V out here? This is XC by square root of R square plus XC square into V. Okay, magnitude. Here this magnitude V in is itself nothing but V in. Okay, peak to peak is given as 10. This V out they given 8. This XC by square root of R square plus XC square into this is 10. 10. Okay. Let us try to rearrange these things here. This 8 by 10 nothing but 0.8. This is nothing but xc by square root of r square plus xc square. Okay. Or let us square on both sides. 0.8 square equal to xc square by r square plus xc square. Okay, r given as 50, we need to find xc. First find xc, and since you know the frequency, then we can find the c value. Right, this is r square plus xc square into 0.8 square equal to xc square. Separate the terms contain xc square. R square into 0.8 square equal to xc square into 1 minus 0.8 square. And this value xc square into 0.6 square. Okay, 1 minus 0.64 nothing but 0.36. Okay, r square into 0.8 square. R into 0.8 we got like xc into 0.6. Everyone got R into 0.8 equal to xc into 0.6. Right. Okay, therefore, what is the xc? Okay, this is 0.8 by 0.6. 0.8 by 0.6 into R. Okay, this is 8 by 3, 8 by 6, 4 by 3 into R given as 50H. Okay, this is 200 by 3. This is your xc. xc nothing but 1 by omega c. Okay, magnitude. Okay, this is nothing but xc only 200 by 3 or 1 by omega c nothing but 200 by 3. Therefore, what is the value of c? C equal to 1 by omega into 3 by 200. Okay, this is c equal to omega. Okay, 2 pi f. 2 pi f into 3 by 200. Okay. It's 1 by 2 pi into 1 kilo h they given to 3 by 200. Simplify it here, take the calculator and try to do. You will get this is 2.387 microfarads. 2.387 microfarads. Let's move on to next question. The circuit shown, the circuit is initially closed and it is open at t equal to 0 and remains there open thereafter. Okay, the time in milliseconds at which the output voltage Vout becomes low is, okay, time, they're asking time at which output voltage becomes low. Okay, so this time they ask. And here no feedback. Okay, it's an open loop configuration itself, open loop op amp. And the open loop op amp, see here this inverting voltage V in connected. Okay, this voltage, the output from here given as the voltage to inverting, and voltage from this section given as a okay to the non-inverting. Let us calculate first of all this one. See here, this is 600 kilo, 400 kilo. Okay, voltage divider network output given to the inverting voltage. Okay, this is 600, 400k, 600k, 400k. This is 5 volts. This is grounded. Okay, this voltage I am giving to the inverting. This is inverting. Then can you please tell me what is the inverting voltage here? Voltage division rule, 400 by that resistance divided by total resistance, 600k plus 400k into total voltage 5. This is 4 by 1000. 4 by 1000 into 5. 4 by 1000. Okay, 4 by 400 by 1000 nothing but 4 by 10 into 5. 20 by 10. This is 2 volts. You got 2 volts. The inverting voltage we got here as 2 volts here. 2 volts. Simply let us calculate the non-inverting voltage also. Here, non-inverting, initially the switch is closed from minus infinity to 0. Circuit is said to be in steady state. Steady state behavior of capacitor is a open circuit behavior. This capacitor is not there. Okay. And right now, this 1 kilo and this 5 kilo constitute the voltage divider network. And this is the V non-inverting voltage. This is 1k, this is 5k. Okay, this is 5 volts. Okay, this is grounded. Let us calculate this V non-inverting voltage. What is V non-inverting voltage? This is non-inverting voltage note. Again, voltage division rule that 5K by 5K plus 1K into total voltage 5. Or this is 5 into 5 by 6. K cancel. Okay, 25 by 6 volts. 25 by 6 volts. Okay, right now you got this inverting voltage 2 volts. Non-inverting voltage, you got it as a 5 by 25 by 6 volts. For all time t greater than 0, for all time t greater than 0, switch is open. Switch is open. Right now, if you notice here, this is a circuit. Notice here. For all time t greater than 0, this switch is open. And if I'm talking about this non-inverting terminal, only this resistor capacitor connected to this network like this. This is inverting. Okay, this 2 volts here. This part of network is there. Okay, and no current flows into the ideal op amp. And here also no current flows into this one. This is a non-inverting terminal. This voltage nothing but 25 by 6 volts. Okay, this resistor capacitor. This is a source-free RC circuit. No external source connected here. It's a source-free RC. Okay, source-free RC circuit. RC circuit. What is for a source-free RC circuit? This initial voltage across this capacitor is 25 volts. We calculated the initial voltage across this capacitor is 25 by 6 volts. For a source-free RC, okay, from circuit theory, we know in transients concept, for source-free RC, okay, when R is there, C is there. Okay. R ohms, C farad, and C initially charged to V naught. Then the response Vc of t is given by initial voltage V naught into e power minus t by tau. Okay, where tau equal to R into C for all t greater than equal to 0. Same way here, this is Vc of t. This Vc of t here, nothing but initial voltage V naught. Okay, this is 25 by 6. So Vc of t 25 by 6 into e power minus t by tau. Tau nothing but R into C. Okay, RC constant. And here this R equal to 5 kilo, C nothing but 0.1 micro, or this is 0.1 milliseconds. This 0.5, sorry, 0.5 milliseconds. 0.5 milliseconds. That's the time constant. And this is the Vc of t or non-inverting voltage here, okay, as function of time t. And we know it's a open loop op amp. Open loop op amp. Okay. So open loop op amp. Okay. And here this voltage. Okay. This Vc of t here. This is nothing but 2 volts itself. Finally, it becomes 2 volts. This 2 nothing but 25 by 6 into e power minus t by 0.5 milli. They are asking us, see the question, determine the time at which the output voltage V out becomes low. Okay, when this output voltage becomes low, when this voltage, okay, we know open loop op amp, when this voltage is more than this voltage, then this saturates to minus 5 volts. When this voltage is greater than this voltage, saturates to 5 volts. When both are same, okay, output is 0. Okay? Right. Therefore, rearrange this one. This is 12. This is by 25 equal to e power minus t by 0.5 milli. Rearrange and find the t. The t will give that value. Okay, this e power when goes to that side becomes ln. Okay, this is minus t by 0.5 milli. And goes to that side, e power becomes ln 12 by 25 base e. Okay, and minus when I multiply here, then a t by 0.5 milli will become ln of 25 by 12. Okay. Therefore, t is t equal to that 0.5 milli into ln of 25 by 12. Okay, see, okay, please tell me, calculate that value and tell me here. 0.5 milli into ln of 25 by 12, 0.367 milliseconds. Milliseconds. That's answer. 0.367 milliseconds is right. Okay, now let us move on to the next question. A sinusoidal carrier wave with amplitude AC and frequency FC is amplitude modulated with a message signal M of t, having message signal FM frequency, and this FM is between 0 to FC, much less than FC, to generate a modulated sine wave S of t, modulated wave S of t, given by S of t equal to AC into 1 plus M of t cos 2 pi FCT. The message signal that can be retrieved completely using more envelope detection. Very important. This envelope detection or envelope detector. In envelope detector, we know one point. What is that point? The modulation index should be less than 1. Okay? For envelope detection, modulation index should be less than 1. You substitute one of this value over here. Actually, this S of t, nothing but AC into 1 plus that Ka into M of t, you know that one, Ka into mu, okay, something into cos of 2 pi FCT will get here. This Ka is the sensitivity, okay, and mu. We substitute Ka equal to 1 and just try to check this value of mu by substituting all these frequencies. Okay, this AC 1 plus M of t, AC 1 plus M of t cos of 2 pi FCT. Okay. Actually, it seems like a AC into 1 plus that Ka nothing but 1 if you substitute 1 mu. Okay, Ka into mu. Something you are getting here. Let us take Ka equal to 1. Okay. It seems like AC into 1 plus Ka into mu. 1 into mu. And right now you substitute these values here instead of M of t, you place these values. And tell me which signal will give mu as less than 1. Here, directly by seeing these amplitudes, we can identify. Okay, if I substitute 2, this mu I'm going to get 2. If I substitute this to mu, I'm going to 2. If here this 2, mu I'm going to 2. Here also mu I'm going to get 1.5. For this case, mu I'm going to get 0.5. And since they are using the envelope detection, okay, for envelope detector, that the envelope detector, when we'll use that envelope detector only when modulation index is less than 1. That's why option C is the right answer. Okay. Option C is the right answer. Okay. Common sense here, no need to do everything complex equations here. Let's move on to next question. Consider 24 voice signals being transmitted without latency using time division multiplexing. If each signal is sampled at, okay, they're given the sample, say, okay, 12 kilohertz, and that represented by 8-bit words. Okay, the bit duration 24 voice signals. Okay. The bit rate. Okay, if you want the bit rate is represented by RB. Okay, and bit duration TB. They are asking TB. They are asking TB. TB nothing but 1 by RB itself. First of all, bit rate. What is that bit rate? RB nothing but given 24 signals. Each one is 8 bits and sampled at 12 kilohertz. Okay, 12k. Then what is value 24 into 8 into 12k? Calculate. You are going to get 2304 k kilo bits per second, kbps. Or if you want to write in mbps, this is 2.304 mbps, megabits per second. Then bit duration. Okay, bit duration. This is a TB. This is nothing but 1 by RB. Or this is 1 by 2.304 mega. When it goes to numerator, becomes micro. Mega denominator goes to numerator, becomes micro. Or this value, calculate and tell me 1 by 2.304. Take your calculator and tell me the answer. 1 by 2.304. 2.304. What is value? This is 0.434. Okay, microseconds is the right answer. Microseconds. Okay. Next question. A capacitor is constructed using two concentric spheres, and A is the dielectric. Okay, they given something like that. Two concentric, like this. Mediums. Okay. Dimensions they given A, B. A is 10, B is 15, A greater, A less than B. Okay, let us this is A, this is B. Okay, A is 10 centimeters, B is 15 centimeters. The capacitance in picofarad up to 2 decimals is. Okay. And here directly I'm giving the formula for two concentric spheres. Two concentric spheres like this. Okay. This capacitance can be calculated 1 by 4 pi epsilon 1 by A minus 1 by B. Or this is 4 pi epsilon by B minus A by AB. Or this is capacitance nothing but 4 pi epsilon A into B by B minus A. Just substitute those values, that's all. This is 4 pi into epsilon 8.854 10 power minus 12 farad per meter into A 10 centimeters given. Convert into meters. This is 10 power minus 2 meters. This is also 10 power minus 2 meters. Okay. 10 power minus 2 15 into 10 power minus 2 divided by B minus A. Okay, 15 minus 10, 10 power minus 2. 10 power minus 2 and 10 power minus 2 getting cancelled. Okay, rearrange these terms, you will get something like 33.33 pico. This is a question given from EMF, electromagnetic fields. Okay, some question from mathematics. Matrix is given. If M equal to which of the following statements is or correct? This is MSQ question, multiple select question. Okay, MSQ. Actually, this is row 1, row 2, row 3. By observing here 2, 3, 7, this is 4, 6, 14. Okay, this is twice this one. Okay, if I operate something like R3 equal to R3 minus 2 R1. Okay, then this is 2, 3, 7, this is a 6, 4, 7, and this becomes 0, 0, 0. 4 minus 4, 6 minus 6, 14 minus 14. Okay, this becomes 0. Okay, that's why, okay, this determinant, if I calculate, this is M, determinant of M, this determinant of M becomes 0. Then rank is not equal to rank of M, not equal to 3. So 3 by 3 matrix, rank cannot be 3. Then we'll select any 2 by 2, we'll see the rank of that. Okay. Determinant of that 2, 3, 6, 4, if we calculate 2, 3, 6, 4, this is 8 minus 18, this is minus 10, not equal to 0, rank of M equal to 2. Rank of M equal to 2. Okay. Right. Determinant also 0. The rows of M are linearly independent. Okay, wrong. Row, everything is 0. These are dependent rows. 2, 3, 7 twice. Okay, you got 4, 6, 7 rows are linearly independent. Therefore, options for this one are A and D, both are correct. A and D both are correct. Next question. Consider the differential equation dy by dx plus y into ln of y equal to 0. And they given the initial conditions y of 0 equal to e. Then they're asking what is y of 1 here. Okay. So here this also simple only dy by dx, okay, plus y into ln of y is given as 0. Or directly this dy by dx we can write as minus y into ln of y. Okay. Or separate the terms containing y, separate the terms containing x. Therefore dy by y, okay, minus y ln of y, ln of y equal to dx itself. Let's put the dx here. This again I'm writing this dy by y into ln of y equal to minus dx. Okay, let us substitute let, okay, ln of y, assume it as some t, then 1 by y dy will become dt. Yes or no? Therefore notice here this is t 1 by y dt. Okay, t dt. This is minus dx. Okay, ln of y. Okay, I'm assuming ln of y as t. This is 1 by t. 1 by t dt. Okay, this is nothing but minus dx. Let us apply integration on both sides here. 1 by t dt equal to integral minus dx plus some constant here. Okay, this is ln of t equal to minus x plus c. Okay, and what is the t here? T nothing but ln of y equal to minus x plus c. And what is given? Given y of 0 equal to e. Let us evaluate that c value. since y of 0 equal to e, or y value equal to e when x equal to 0, right? ln of e, actually y equal to 0 plus c. ln of e nothing but 1, this is 0 plus c, or ln of 0 of 1 is nothing but 0 plus c value we got as 0. This ln of y minus x plus c, since ln of y equal to minus x plus c, and c value we got as 0. Okay? Therefore, we got ln of y equal to minus x, or ln of y equal to e power, this is base e, right? E power minus x, or y equal to e power minus x. This is a solution for the given question. But what they asked us to determine, they asked us to determine y of 1. Okay, this y of 1, substitute to, okay, x equal to 1, y of 1 nothing but y value at x equal to 1. Therefore, y equal to e power minus 1, or e power 1 by e. Okay, option B is the right answer. Simple question from mathematics. Okay, next question. The Newton's-Raphson method is applied to determine solution of f of x equals 0, where f of x equal to x minus cos x. If the initial guess of the solution is x not equal to 0, the value of the next approximation x1 is. Here we know one thing, Newton-Raphson's method. Raphson's method. Okay, what is that Newton-Raphson's method? Here, that in Newton-Raphson method, this x1 can be written as x naught minus that f of x naught divided by f dash of x naught. First approximation, okay, you can calculate this. At f of x equal to 0, okay, they given the initial value. At 0, they given that 0. Okay. What is that f of x? This f of x at 0, they given like f of 0 equals 0, yeah? And what is f of x given? F of x given as x minus cos x. Then what is f dash f x here? This is 1 minus sin x, okay? And this is nothing but 1 plus sin x. Okay, right. This x1, let us substitute the first one. 0 at 0, f of x, okay, x minus cos x divided by 1 plus sin x at x equal to 0. This also at x equal to 0. Okay. Or this is x1 value. Tell me, numerator, okay, 0 minus, this is 0 minus cos 0, 1 divided by 1 plus sin 0, 0. Or this x1 nothing but 0 minus 1 by 1. That implies this x1 equal to 1. That's the first approximation. That's all. Answer for the given question nothing but 1 is the right answer. Okay, the matrix A is given as 4, 3, 9, minus 2. Has eigenvalues minus 5 and 7. Okay, here even they not given the eigenvalues, we can write. Okay, if A minus lambda I, a matrix determinant equals 0. Like see here, this is 4 minus lambda 3. This is 9 minus 2 minus lambda. Okay, substitute determinant equals 0. Then you'll get two values. Okay, you'll get minus 5, 7. Okay. It's eigenvalues. They already given this one. The eigenvector is R. This is also MSQ question, multiple select questions. Okay, more than one answer is right. So here we know one thing. Okay, this A into X always equal to lambda into X. Okay, these vectors. Okay, these vectors, they will obey this eigenvalues like this. A into X equal to lambda into X. If I take the first thing, vector A, okay, sorry, this matrix A, 4, 3, 9, minus 2, let us substitute here. I'm taking this first one as 1, 1. Okay, 1, 1. Multiply and tell me what is this value. This is 4 plus 3, 4 plus 3. And this is 9 minus 2. You got like 7, 7. This 7, 7 can be written as 1 into 7 into 1. It seems like a, see here, this is X. This is lambda into X. Right? We got A into X equal to lambda into X. Okay, X is a vector. Okay, this x is 1 1. It is satisfying here. This is satisfying. Let us take the second. 4 3 9 minus 2. Okay, into let us take the third 3 4. Let us multiply this one. This is 12 plus 12. This is 27 minus 8. 24. Okay, this is 4 3 is 12. 3 4 is 12. 12 plus 12. Okay, this is 19. And it is not following any relation. Okay, here a into x not equal to lambda into x here. Okay, not satisfying any relation. Let us take the C option. This is 4 3 9 minus 2, and a vector here. This is 3 minus 6. Okay, let us multiply. Tell me, this is 12 minus 18. 12 minus 18 minus 6. This is 9. 27 minus 12. 27 minus 12. 15. This also not following any particular thing. Okay, not following anything here. 3 minus 6. Okay, here this is, please correct this one. This is given as 2 6 here. 2 6. If you take this is 2 6, tell me 2 6. 2 6. This is 8 minus 18 minus 10. This is 18 minus 12. 18 minus 12. 6. Okay. 18 minus 12. 18 minus 2. 18 okay, right? This is 18. This is minus 12. 18 plus 12. Okay, 30. 18 plus 12. This is 30. Okay, or if I take the minus 10 common, 5 common. Okay, if I take 5 common or minus 5 common, it seems like 2 minus 6. 2 6. Okay, 2 minus 6. Here also it seems like a into x equal to lambda into x. Okay, and for this 2 minus 6 here, and the lambda is minus 5 we got here. This is satisfying. Okay, this is also right. And if I consider, okay, if we consider fourth option, okay, 4 3 9 minus 2. Okay, this is 2 8. 2 8. Oh, please tell me 4 8. 8 plus 24. This is 18 minus 16. Okay. This value, what is value? 32. This is 2. And this is, if I take 2 common, 8 1. Not following anything. Okay, not lambda into x. That's why option A and C are correct. A and C for this question. Yes. Okay, next question. A, C. Okay, option A, C are correct answers. Change this option here to minus 6. It is given in the GATE question. Given f of z equal to 1 by, okay, they're asking us to determine the residue at 1 point. Okay, how to find residue? Residue. Okay, residue, if you want to find residue at this point, you multiply that one. Okay, that function. Z plus 1, okay, Z plus 2, Z plus 3. Okay, substitute Z equal to minus 1. That's all. This is 1 by minus 1 plus 2 into minus 1 plus 3, and this is 1 by 1 into 2. Okay, answer. That's all. Right. Okay, hope you have learned something, okay, from this session. And this I prepared based on the memory based questions sent by most of the students throughout India. Okay, and the GATE paper will out within 1 week or 2 weeks. Okay, and this session was conducted by IIT on February 6th afternoon. Okay, all the best everyone. Thank you. Bye. God bless you all. Jai Hind.